My name is Svetlana Koleva. I'm from University of Russia, Bulgaria. I present you my article Analysis of Thermal Deformations in the Machine-Fixture-Tool-Part System during Turning of Details. At the precise technological transitions in processing the details, the influence of thermal deformations can be decisive in ensuring the accuracy of the dimensions of the surfaces. Accuracy management requires that the technical and organizational measures related to errors from thermal deformations be identified at the technological design stage. Thermal deformations and their influence on dimensional accuracy are the subject of scientific research in search of approaches to their reduction, management, and compensation. All components of the processing system are subject to heating and therefore generate error from thermal deformations. The figure shows the factors that influence the thermal deformations and necessitates the making of specific technological decisions according to the specific processing conditions. Before clarifying the possibilities for predicting and controlling the thermal deformations, it is necessary to create a simplified model explaining the physical nature and parameters of this process. The components of the machine-fixture-tool-part system differ from the idealized model in the following, which are shown on the slide. All these features are a prerequisite for the idealized model, not allowing adequate assessment and prediction of thermal parameters. In asymmetric bodies, heating and accordingly heat transfer to the environment will not be the same, which is why different points on the body will have different temperatures. Figure 2 shows the general distribution of heat in the housing of the spindle assembly of a late CE 063 from the front side of the spindle. Due to the real asymmetry in the heat distribution, zones of different temperatures arise, limited by isolines. The housing is mounted to the machine body and is therefore a not free heated body. In reality, the housing is not a solid body. This causes variation in the heat transfer coefficient. In real machining processes, the machine load regime is variable, which also creates a variable thermal load. In addition, there are planned and unplanned interruptions that change the exponential shape of the thermal deformations described by the theoretical model. Fluctuations in ambient temperature, including that of the coolant, lead to variation in the heat transfer coefficient. Based on the analysis, the sources of thermal impact on the machine-fixture-tool-part processing system are divided into the following 6 groups. All these sources have an impact on the machining accuracy. They can interact with each other, affect different parts of the machining system with contradictory effects, and therefore altogether create an uneven temperature field in its structure. To analyze the factors which have an impact on the thermal deformations, laboratory and natural studies were carried out. You can see the conditions of the experiment. The analysis of the results of the presented and other experiments and observations conducted is the basis of the following conclusions. Changing ambient temperature, the lubrication cooling fluid temperature, and on the workpiece temperature, they follow a trend with a certain inertia. The temperature of the workpiece follows that the coolant fluid temperature while maintaining a difference from 2.5 to 3 degrees Celsius, which lowers to 1 degree Celsius with sufficient flow rate. The ambient temperature determines the temperature of the measuring device, and the lubrication cooling fluid determines the temperature of the part during its measurement. When processing parts without applying special measures to reduce the influence of thermal processes, accuracy of 6 to 8 grades requires periodic calibration of the measuring instrument and recording the temperature of the parts. Figure 4 presents results of measuring the temperature of the working space in a real production process. A part made of nodular iron GGG50 is processed with cooling and operation duration of 8.5 minutes and interruptions for changing, setting and adjusting 0.8 minutes. The measurements are carried out before changing the workpiece. The change of the temperature of the working environment is within 11.5 degrees Celsius. The increase in the intensity of processes and accordingly thermal deformations lead to an increase in auxiliary time for more frequent control and corrections, time and energy consumption for preheating the machine, impossibility or loss of time for developing software compensation for angular thermal deformations. Furthermore, these errors are not stationary and special tuning algorithms are required to compensate for their dynamic part. In this regard, it is necessary to use or combine the traditional approach to compensate for errors with modern methods built through the modeling of thermal errors. The solution from the analysis of the applied approaches are given in next two figures. They are grouped into technical and technological. Technical ones are those that reduce thermal errors with constructive solution and providing a suitable working environment. Figure 5. Technological solutions are related to compensating thermal errors based on information from accuracy control. Figure 6. The impact of thermal deformations on the resulting size is manifested as a relative displacement between the dimensioning axis and the dimensioning element of the tool. To define this, it is necessary to introduce a base in the considered direction, x, from which thermal displacements are taken into account. For such, it is justified to choose the design basis of the machine. It is located on the carriage. Figure 7a, and determined the mutual position of the spindle and crosslight. Figure 7a shows the dimensional relationship as the radius of the machine surface, measured immediately after machining, is obtained from the dimensions specified in relation to the design base of the machine. The height realized during cutting passes mainly into the chips and the rest into the tool and workpiece. Most of the height generated is absorbed by the coolant and the other is emitted through convection and evaporation into the working environment. It is the air environment of the closed zone of the machine in which the temperature is higher and has increased humidity and leads to a significant increase in the temperature of the elements of the processing system located in the zone. An important feature of the working environment is the large temperature gradient, which is highest in the processing zone. In this sense, the coolant and the air environment of the working zone are carries of the heat created during cutting. Because the ambient temperature is lower than the heated elements of the processing system, it has a mainly cooling effect. The dimensions shown in the figure limit certain elements of the processing system that create the composite thermal errors in it. Dimension A covers part of the body and the spindle assembly. The table shows the influence of the various thermal factors. The minus sign in front of the sum of them reflects the cooling effect of these environments. The angular displacements on the spindle axis of rotation is shown in Figure 8. As a result of the theoretical and experimental studies in this paper, these conclusions can be made. Thank you for attention.